All right, well, welcome everyone to another GRE Prep Hour. I am your host, Tyler. We'll be talking about divisibility connections today. The way these prep hours work is we are live in a Zoom room right now, but we're also going to record this and host it on YouTube later. So welcome to everyone, whether you're live here now or watching this on the internet at some point in the future. If you're here in the room with me right now, in the Zoom chat box, why don't you tell me where you are currently located? I'm in Brooklyn, New York right now, and it just got very hot here this week. I hope y'all are surviving and having nicer weather wherever you are. All right, we got someone from Texas. I used to live in San Antonio. Go Spurs. Okay, first thing we're going to do here is I'm just going to show you all a practice problem, and I'll give you a couple minutes. Once you have an answer, if you're here in the Zoom room, chat it to me in the box, and then we'll go over this together. So here is your first problem. So one thing you'll need to do to get good at this exam is kind of learn the different coded language the test writers will throw at you. So here we've got this problem, and it's saying how many positive integer values of x is 42 divided by x, an integer. So kind of this mouthful of words, but ultimately what you want to recognize when you start saying this language where you have some integer divided by an integer and it results in another integer, it's testing this concept of divisibility. So for example, because 15 divided by 3 is equal to 5, we could express this in a number of... Sorry, I realized I was muted right there. let me start that spiel over. So to get good at this test, one thing you need to do here is get used to the different sorts of coded ways that the GRE test writers might present different concepts. So in this original problem, they have this language, how many positive integer values of x is 42 divided by x, an integer. So in terms of language, if you have an integer divided by an integer and that produces another integer, this is all related to this concept of divisibility. For example, 15 divided by 3 produces the integer 5. That means 15 is divisible by 3. I could say 15 is a multiple of 3. 3 is a factor of 15. 3 is a divisor of 15. 3 divides 15 evenly. 15 divided by 3 leaves no remainder. They're all just different ways of expressing the same idea of this number is a factor of another number. By the way, all these on right, these are the ways to kind of say the opposite, that something is not a factor. So if I go back to the original problem here, this is essentially asking me how many factors does 42 have? So if I'm trying to find factors of a small number, I can do that manually by building a factor table. So basically, I'm just going to draw out this number 42, put a line under it, and then I'm going to start with 1 and the number itself, because those are always going to be factors of any number. So 1 and 42. And then what I want to do is increment the left column. So increment 1, I try 2. Does 2 fit into 42? Yeah, 2 times 21 makes 42. Then I'm going to keep incrementing. I try 3. Does 3 fit into 42? Well, 3 times 15 is 45. So 3 times 14 is 42. And I'm going to keep incrementing. Does 4 fit into 42? Nah, 4 goes into 40, but not quite 42. 5 also goes into 40, but not 42. 6 works. 6 times 7 is 42. And then I increment again. At this point, as soon as you have overlap between the two columns, I've got a 7 in the left and a 7 on the right. As soon as there is overlap, you're done. Don't have to go any further. You've found every possible factor pair. So there are 1, 2, 3, 4, 5, 6, 7, 8 possible integer values of x that are positive that make 42 divided by x another integer. So another really common factor idea is something we call prime factors. So let me just give this one to y'all without any other information. Chat me your answers for this one. Okay, so quick definition here. Primes, how do we define a prime? So primes have exactly 2 positive factors. Because of that, 1 is not prime. It only has one factor. And the smallest prime is 2, right? Its factors are 1 and 2. It has exactly 2, so it's prime. Another fun fact about 2 is it's the only even prime. Every other prime out there is odd. The next ones would be 3, 5, 7, 11, 13, 17, 19. It's good to kind of have these numbers, be able to rattle those off the top of your head, the first few primes up to 19. Get tested a fair amount on this exam. In the previous problem, we saw how to count positive factors using a table. To find prime factors, what I want to do is build a tree. So I'm going to start with 20, and I can split 20 into any 2 factors. I don't want to use 1 in itself because I'm specifically hunting primes now. So anything besides 1 in itself. So I'm going to do 2 and 10. Anytime I get a prime number, like 2, I put a circle on it. That indicates that branch of the tree is done. And I'm going to keep going. I can split 10 into 2 and 5. And at that point, every branch of this tree has a circle on it. So I've prime factorized it, and I can answer the question, how many unique prime factors does 20 have? So we've seen 20 is equal to 2 times 5. The answer to this problem is going to be 2, specifically because of this word unique. Whenever they ask about unique versus distinct primes, you're only going to count unique instances. So I count the 2, I count the 5, that's it. If this problem instead got rid of that, if it was just asking how many prime factors does 20 have, then the answer is 3. Because I think of both the 2's and the 5. 1, 2, 3. So a sneaky, kind of subtle distinction you want to be aware of: unique prime factors versus total prime factors. Make sure you read those question stems carefully. So let's try this again with a bigger number. I want you to figure out how many unique and how many total prime factors the number 420 has. Same thing here. We're going to build a tree off of 420. So first factors that come to mind are 7 and 60. 7 is a prime, so I'm going to circle that. breaking up 60, I think I'd go with 6 and 10. And I can break each of those down further. So 6 into a 2 and a 3. Both of those are prime. And 10 into a 2 and a 5. So how many unique prime factors? Well, let's start with total first. So total, we've got a 2, another 2, a 3, a 5, and a 7. So we have 5 total prime factors. But for unique, I only count a single 2. So 4 unique, 5 total. Okay, let's try a quantitative comparison next. Give you all 3 minutes with this one. So from the upfront info, we know n is going to be between 61 and 67. So I can really whittle n down to 5 different values, right? Between 62 and 66, and it's an integer. Quantity A is pretty verbose here. The number of integers greater than 1 and less than n that are factors of n. But notice how similar that is to our definition of a prime, right? If something is prime, its only factors are 1 and the number itself. And here we're looking for factors other than those. So essentially, we're kind of looking for non-prime values here. Let's look more at what happens to our number of factors. So if n were 62, then I do have some other factors there besides 1 and 62 itself, right? 2 and 31, those are also factors of 62. Likewise with 63, in addition to 1 and 63, which I have to ignore, we could have 3, 7, 9, or 21. So far, this tells me quantity A, if n were 62, quantity A would be 2, because I have 2 factors other than 1 in the number itself. If n were 63, quantity A would be 4. It's got 4 factors other than 1 and 63. And if I keep going through this, no matter what we do, all of these numbers are not prime. So I'm always going to get factors other than 1 and other than n itself for all the possible values of n. Which is all to say, quantity A must be bigger than quantity B. I always get more than 1 factor for quantity A over here. Something else interesting about this problem, if I ignore that bit from quantity A, and if I reintroduce 1 and n itself for a moment, notice what's going on with the total number of positive factors for n. If n is 62, I have 4 positive factors there. If n is 63, I have 6 positive factors. If n is 64, we're going to get 7 factors. If n is 65, 4 factors. If n is 66, 8 factors. And I want to highlight 64. We get 7 positive factors here. That's the only one that's odd. We get an even number of prime factors for every other choice, but 64 is producing 7 positive factors. Why is that? What's unique about 64 compared to the others? Well, what's unique is that 64 is a perfect square. So perfect squares always have an odd number of positive factors. Right? Like 1, it only has 1 factor. 4, 1, 2, and 4, that's 3 total. 9, 1, 3, and 9, 16. Now, before I mess that up in my head, let me write it out. So we've got 1, 2, 4, 8, 16. So 5 there. If you have a perfect square, it must have an odd number of positive factors. Compare that to non-squares, right? Non-squares are always going to have even numbers of positive factors. Notice that includes primes, because primes, their only factors are 1 in itself. They have to have 2 positive factors, and 2 is an even number. So again, just to reiterate that, primes always have exactly 2 positive factors. So some interesting properties of the number of factors we come up with. And one sort of challenge problem here. Think about this for a second. What kind of number always has exactly 3 positive factors? See if you can use these rules and come up with something that would satisfy that. Give you a hint, 4 is one of them. It has exactly 3, 1, 2, and 4. 9 is another, 1, 3, and 9. 25 is another, 1, 5, and 25. 49 is another, 1, 7, 49. To have exactly 3 positive factors, that number must be a square of a prime. And rarely I've seen that fact come up on the GRE, seen a few questions like that, but interesting number property. Okay, let's do another quantitative comparison. Chat me your answers for this one. 3 minutes. So I would approach this one by testing some cases, picking some values for k. So k has got to be a prime number greater than 2. So the least value k could be is 3. Let's test that out. If k equals 3, then 7k is going to be 21. And how many factors does 21 have? We could have 1, 3, 7, 21. So that is 4 factors. For quantity b over here, again, if k equals 3, then 11k is going to be 33. How many factors do I get there? 1, 3, 11, 33. Again, that is 4 factors. So in this case, quantity A and quantity B are equal. So I've at least got it down to a 50-50. I can eliminate choice A, I can eliminate choice B. And now I want to ask myself, is there a value I can pick for k that's going to break this relationship and make it so that quantity A or quantity B has more or less than the other? And the result we just got, it aligns with this rule, that if I get a non-square like 21 or 33, it's going to have an even number of positive factors. Let's see if I can produce an odd number of positive factors here. So the next value for k I'd want to try is either 7 or 11, because that's going to give me a perfect square in quantity A or quantity B. So if k is equal to 7, 7k is going to be 49. So I've got 1, 7, and 49 as my factors. That's 3. And if k equals 7 for quantity B, I'm going to get 11 times 7, 77. So my factors are 1, 7, 11, and 77. That is 4 factors. So there's an instance where quantity B is greater. The 4 beats the 3. So I found 2 different relationships here. Your answer's got to be D. So another interesting application of primes has to do with finding the greatest common factor and the least common multiple. So say I was trying to find the GCF of 24 and 36. There's a way I could do that manually, but if I want to find a reproducible method here, what I can do is first prime factorize both those numbers, break them down into each of their prime factors. So 24, that's 2 cubed times 3. 36, that's 2 squared times 3 squared. And then to find the greatest common factor, what I want to do is take the lowest incidence of each factor. That means I've got factors of 2s, I've got factors of 3. I want to take the lowest of each of those. So my lowest 2 is the 2 squared. My lowest 3 is the 3 to the first. I'm going to take those 2 values and multiply them together. That gets you the greatest common factor every time. And it's a similar process for the least common multiple, but it differs in the final steps. So if I'm trying to find the least common multiple of 24 and 36, first thing's the same. I prime factorize each. But to find the least common multiple, I want to take the largest incidence of each factor. So my largest factor of 2 is the 2 cubed. My largest factor of 3 is the 3 squared. We take those 2 numbers, multiply them together, we get our LCM, which is 72. So 2 very related concepts, but we're kind of grabbing the opposite sets of numbers. And be aware, it's a little counterintuitive that with the greatest common factor, we take the lowest incident, and with the least common multiple, we want the largest incident. So there's that little kind of cross wiring there. Don't get tripped up on that. So here's a question I want you all to try on your own. Find the greatest common factor of 216 and 480. So 216 is a very special number. It's a perfect cube. It is 6 cubed. So to prime factorize that, I can just break that apart into 2 cubed times 3 cubed. 480 is a little more complicated. I'd build out a full tree to prime factorize that one. And when we do, we see there are 5 2's. So 2 to the 5th times a 3 to the 1st times a 5 to the 1st. And now what I want to do is take the smallest incidence of each factor. So the smallest 2 is the 2 cubed. The smallest 3 is the 3 to the 1st. And then be careful. Although there's only one 5 here, there's this implicit 5 to the 0 power. So whenever something lacks a factor outright, remember that there's this implied 0th power. So I want to take the 5 to the 0. That's smaller than 5 to the 1st. So now I combine all of these. My greatest common factor is 2 cubed times 3 to the 1st times 5 to the 0. So that's going to be 8 times 3 times 1, or 24. And that's our answer. Okay, as an aside, what would the least common multiple of these two numbers be? To answer that, you'd take the highest incidence here. So I'd take the 2 to the 5th, the 3 cubed, and the 5 to the 1st. So those three multiplied together. That's going to get you this big number, 4,320. But that's the least common multiple. Let's see how these processes might show up in a word problem. Give this one a shot. This one is a least common multiple question in disguise. So we've got this machine that periodically does 3 different things. And eventually they all line up and happen simultaneously. And then we want to find from that point, when's the next time all 3 of these numbers line up again. So I want to find the next multiple all 3 of these numbers have in common. Same process though, we're going to prime factorize each number. So 22, that's 2 times 11, 18, 2 times 3 squared, 45, 3 squared times 5. From here, take the largest incidence of each factor. So from the 2's, it's really the same. They're both 2 to the 1, so we're just picking 2 to the 1. From my 3's, the biggest is going to be 3 squared. From the 5's, I've only got the choice of the 5 to the first. Same for my 11's. So my LCM, it's going to be 2 times 3 squared times 5 times 11, which is 10 times 9 times 11, which is 10 times 99, which is 990. Your correct answer there. Okay, an extension here. What's the greatest common factor of 22, 18, and 45? So to find my greatest common factor, I take the smallest incidence of each of these. So I take the 2 to the 0. Remember, don't forget those implied 0 powers. My 3 to the 0, my 5 to the 0, my 11 to the 0. So that is all to say 1 times 1 times 1 times 1. Greatest common factor is 1. There's nothing higher than 1 that those 3 values have in common as a factor. So little sneaky, but just 1. Okay, at the beginning of this lesson, we talked about how we can use a factor table to count factors, which is handy for small numbers, but what about when I want to calculate the number of factors that a big number has? Let's first model this with a small number, because there's a trick I can use that's really more efficient than trying to count manually. So if I'm trying to find all the positive factors of 24, there's a 3-step process here. First thing I want to do, list the prime factorization. Surprise, surprise. 24, it's 2 cubed times 3, 8 times 3. So the exponents here, we've got an exponent of 3 on the 2. I've got an exponent of 1 on the 3. What I do next is add 1 to each of those exponents. So the 3 becomes a 4, the 1 becomes a 2. Then you multiply those values. 4 times 2 is 8. That's our answer. 24 has 8 positive factors. Now, why does that work? Well, this is because every single positive factor of 24, it's got to be built off those prime factors, right? Prime factors are essentially the building blocks of any number. The reason I add 1 is to account for that 0 power. So every factor of 24, it's going to have a prime factor of 2 with an option of 2 to the first, 2 squared, 2 cubed, or 2 to the 0. That's 4 options. That's why I have to add 1 there. Same for the factor of 3. Every positive factor of 24 is going to have a factor of 3 that's either 3 to the first or 3 to the 0. We're kind of visualized in matrix form here. Here are those 8 factors with either 2 to the 0, 2 to the first, 2 squared, and 2 cubed from the 2's, or a 3 to the 0 and a 3 to the first. as their power of 3. So again, 1, list the prime factorization. 2, add 1 to each exponent. And 3, multiply the new values together. That's how we can count the factors in a more reproducible way, which comes in handy when we're trying to find the number of factors of something large that would be a real pain to try and list out manually with the table. Let's try this one out. How many positive factors does 1800 have? First thing to do here, prime factorize 1800. It's a big number, but we can split it into smaller ones, 18 times 100, right? And then just keep prime factorizing using the tree from there. And we should get that 1800 is equal to 2 cubed times 3 squared times 5 squared. From there, I'm going to add 1 to each exponent. So we take that 3, that 2, and that 2, add 1 to each. 4, 3, 3. Now we just multiply them together. 4 times 3 times 3 gives us the answer. 1800 has 36 positive factors. All right, next thing we're going to do. More factor stuff. No surprise there. This one's kind of like a hybrid of pure math and a word problem, which is interesting, but see if you can unpack this and then we'll take a look together. So another pretty dense one here. But notice, for something to be divisible by 24, it also has to be divisible by the prime factors of 24. So 2 cubed and 3. So let's assume for a second, if n cubed was exactly 24, then n itself would be the cube root of 24. So the cube root of 2 cubed times 3. But we have an issue. The cube root of that simplifies to 2 cubed times the cube root of 3. And that is not an integer, which violates this rule up here that n must be an integer. So what's going on is that n cubed itself has to be something bigger than 24. Specifically, I shouldn't say specifically, I should say more generally, this is the rule that's going on here. that if n is an integer, then the prime factors of n to the x, the prime factors must all have exponents that are multiples of x itself. So this prime factorization, 2 cubed times 3, it can't be the prime factorization of n cubed because there's not enough cubes there, right? I have a 3 to the first. I would need every exponent in that prime factorization to be a multiple of 3 because we're cubing it. It's got to be a 3, a 6, a 9, a 12, something like that. Therefore, if n is an integer, n cubed isn't just divisible by 2 cubed times 3. It has to be 2 cubed times 3 cubed. That's the sort of smallest I can make n cubed in order to get those multiples of that exponent, right? We're cubing everything. So all those prime factors have to have exponents of 3 or a multiple of 3. So from here, I can say, okay, if n is equal, n cubed, if n cubed is equal to 2 cubed times 3 cubed, now if I uncube that, then n is just going to be the cube root of that whole thing. And the cube root just undoes the cubes, and we get 2 times 3, which gives us 6. So 6, that's the biggest number that must be a factor of n here. Okay, let's check out one more similar one just to drive this point home. I know this is a pretty counterintuitive rule, but an interesting number property. Try out this next problem. First thing here, examine the prime factors of 27. 27 is a perfect cube. It's 3 times 3 times 3, 3 cubed. So examine for a moment, what if k squared were exactly 27? If k squared is 27, right, 3 cubed, then k itself would be the square root, right? We just undo that square on each side. It's the square root of 3 cubed. But 3 cubed doesn't unsquare nicely. I'd get 3 root 3. That is not an integer. Again, we need to keep k as an integer. So because I'm squaring k here, it's got to be divisible by 27. What I need to do is bump up that prime factorization one so that it becomes a multiple of 2. So instead of 3 cubed, I need to bump it up to 3 to the 4th. Now a 4th is something that'll unsquare nicely and result in an integer. So if k squared is 3 to the 4th, undo the square on each side, take the root. K itself would be 3 squared, which is equal to 9. And that's our answer. 9 is the largest number that must be a factor of k. So whenever you're in these funky situations where something is defined as an integer and then we're looking at powers of it, you want to make sure the prime factorization, every exponent in that prime factorization must be a multiple of whatever power we're raising it to. So if it's a square, every value in the prime factorization must have an exponent that is an even number, because all even numbers are multiples of 2. Okay, so we're at the end of the prep hour here. So take a minute, pause and reflect, see if you can recall some of the big ideas we talked about today. For me, there's a few things that stick out. If I'm trying to find the positive factors of a number, if the number is small enough, I can do that manually. I can use a table, start with 1 in the number itself, and then just start incrementing the left-hand side of that table until the left and right columns overlap, and then you found every factor. Alternatively, if it's a big number, then we can use that prime factorization trick we talked about. First thing, prime factorize, take every exponent, add 1, and then you multiply those new values. Handy trick. If I'm trying to find the prime factors of a number, easiest way to do that is to use a tree. Keep splitting the tree until each branch results in a prime at the end. We also talked about some of the interesting properties involving the number of positive factors. For example, primes always have exactly 2 positive factors. Squares will always have an odd number of positive factors, and non-squares always have an even number of positive factors. We also talked about GCF and LCM. Remember, to find your greatest common factor, first thing you do is prime factorize, and then we take the smallest incidence of each factor and multiply those together. Also, don't forget about the 0th power, right? If you have a missing factor, always remember there's a implied 0th factor looming in there that you want to include. For your LCM, similar process, but we take the largest incidence of each factor. And then finally, that last rule we talked about. If n is an integer and we're taking some power of n, every factor in that prime factorization, it needs to have exponents that are multiples of x. So if we square, everything's got to be even. If we cube, everything's got to be multiples of 3. All right, and that concludes today's prep hour. If you enjoyed this and you want to check out some more, visit this link on the screen. If you're in the Zoom room, I'm also going to pop that link into the chat box. That's going to list out upcoming prep hours as well as some of our trial classes. You can register for the first session of our complete 9-session course. And yeah, it's a packed session 1. We get a lot done. It's not just like a boring, cover the syllabus sort of situation. It's 3 hours long and it's going to be jam-packed of great GRE info. So if you're looking for some cool free resources, check that out. And yeah, that's it for now. Thank you all for being here, and I will catch you all next time. Take care.